Paul, you can go ahead.
I'm excited to welcome home to Mizzou virtually. Today's speaker, one of our most accomplished and personally one of my most favorite former students, Dr. Ashlynn Stillwell, who is now an associate professor and the Elaine F. and William J. Hall Excellence Faculty Scholar in Civil and Environmental Engineering at the University of Illinois at Urbana-Champaign. Professor Stillwell was a native Missourian from Odessa, a small town about 20 miles outside of Kansas City. She started as an undergraduate student here in 2001 and earned her Bachelor of Science in Chemical Engineering with an environmental emphasis in 2006. After that, she went to the University of Texas at Austin, where she earned a Master of Science in Environmental and Water Resources Engineering and a Master of Public Affairs in Public Affairs, both in 2010, then finally a PhD in Civil Engineering in 2013. After her education, Dr. Stillwell went to the University of Illinois, where she is now Associate Professor, and currently she is a member of the Water Resources Engineering and Science faculty, and also the coordinator of the Energy, Water, Environment Sustainability Program. Dr. Stillwell teaches courses on water resources engineering, stochastics, hydrology, and water policy. Her signature course, CEE 433, Water Technology and Policy, synthesizes engineering and policy content pertaining to water in an interdisciplinary educational setting, focusing on both technical concepts and communication. Her research focuses on creating sustainable water and energy systems in a policy and relevant context. For her work in this area, she has received the National Science Foundation Career Award and the University's Council on Water Resources Early Career Award for Applied Research. Dr. Stillwell has been proactive in women in STEM activities, even in the short few years when she was working on her tenure, which, as many of us might attest, is no small feat and shows a lot of dedication to the cause. As a result of her work, she was honored with the 2015 Girl Scouts of Central Illinois Women of Distinction Award in Science, Technology, Engineering, and Mathematics, STEM. She now serves as chair of the board of directors for the Girl Scouts of Central Illinois and was previously chair of the board of directors of Faith in Place. Dr. Stillwell is an outstanding teacher and mentor of her students. She received the 2018 Rose Award for Teaching Excellence and the 2018 Association of Environmental Engineering and Science Professors Award for Outstanding Teaching in Environmental Engineering and Science. Dr. Stillwell has also been among the list of teachers ranked as excellent by their students in Illinois. But I have to admit though, I did not find the time to check her score at ratemyprofessors.com. Did you, Ashlynn?
I did not. I'm not brave enough to do that.
You should. Dr. Stillwell's seminar today is Data-Driven Sustainable Cities, Energy and Water in the Urban Environment. Dr. Stillwell.
Thank you so much. Okay. Hopefully you can see my screen. Let me fiddle with some things so I can see. All right. So today I'm going to talk a little bit about the work that I've been doing at Illinois on sustainable cities and specifically around water and energy in the urban environment. And urban is something that I think depends on context personally. As Dr. Chan said, I grew up in a small town. I grew up in Odessa, Missouri. And so what defines a city to me is honestly anything more than about 2,000 people. But in the context of the Midwest, that could be a small town by some standards and could be not necessarily an urban setting. And so urban could encompass something like Kansas City or St. Louis or Chicago, but also some of these medium-sized cities and smaller cities or towns. Oops, hang on. So when I think about the urban environment, this is kind of a conceptualization as we think about water in cities and the relationship that energy has with water in cities. And if we focus on what comes into the city, there's water supply, and the water supply has some energy associated with it for water sourcing, acquisition, and also treatment. And then that water travels to some consumer, a residence, an industry, or a commercial entity. And not all of it makes there, not all of the water, excuse me, makes it to that particular customer, and we call that non-revenue water. And because we've put energy into the water system, any water that doesn't make it to a customer or is accurately metered and paid for, considered non-revenue water, has some embedded energy loss associated with it. And the flow of water then to the urban environment or the built infrastructure of the environment then becomes wastewater. I apologize for the lack of contrast between brown and black, but my student who made this figure thinks it's funny. So we color coded these things to have wastewater as brown and water supply as blue. So some of that water becomes wastewater effluent. And we also have the natural interaction of water in the built environment as rainfall that might become stormwater runoff. These are two separate arrows here in this figure, but in some instances, those could flow in one pipe in the case of combined sewers. So this wastewater effluent and stormwater runoff could be together in the same infrastructure, or they could be separate. But there is a link between them, even in those separated sewer systems where wastewater effluent is directly influenced by rainfall through infiltration and inflow. And one of the things that has been discussed a lot in the context of sustainable cities is this concept of the circular economy. And on the water side of things, that comes through water recycling, which we draw here as this purple arrow that's coming back to the water supply. And that could represent a lot of things. That could be non-potable water reuse for irrigation in the urban environment. That could potentially be recharging some drinking water source in an indirect potable reuse system, or this purple arrow here might not exist at all. And what was once drinking water that became treated wastewater effluent that was discharged to a stream simply then becomes drinking water sources for downstream communities through some sort of de facto reuse. And so this is our conceptualization of water in cities and the water economy of cities. And in this investigation, and a couple of questions I kind of want to touch on today is some work that my now former PhD student did on water and energy sustainability in cities. And so when we first started this investigation, our question was, how do we characterize these urban water systems in US cities, which might seem fairly straightforward, but turns out there's not a lot of information on this particular question. And then our next follow-up question is, how does water and energy relate to different material flows in and out of US cities? As we think about these sustainable cities, a lot of times what comes up are things like smart street lighting or smart mobility in autonomous vehicles. But there's a lot more to the sustainability of a city because there are different flows of materials going in and out and potentially recirculating. So we wanted to understand how water and energy play into that perspective. So let's start with the first question on characterizing urban water systems in US cities. And we wanted to do a data-driven approach to what was happening with water and energy in cities. And so we asked ourselves, what data are out there on urban water? Well, there's a fair amount, but turns out none of them are really all that great for what we were trying to do. The USGS, US Geological Survey, does the National Water Census, where they estimate water withdrawal on a county scale every 5 years. And that's based on different sectors of the economy. So that includes things like thermoelectric power generation, irrigation, domestic and municipal water withdrawals. And that's great, except it only considers things that happen within the county, not things that cross county boundaries. And so that might work for something in Boone County, but it won't necessarily work for estimating water flows to, say, Los Angeles, a large city that sources water from hundreds of miles away and bringing in these long distance water sources. So that's some information, but it's not really getting at what we were interested in at the city scale. Other sources of water data are Circle of Blue. They're a nonprofit organization that mostly focuses on water pricing. And on approximately an annual basis, Circle of Blue will report different prices of water and wastewater services across major US cities, but again, not really focusing on energy and flows of water and wastewater that are treated. The American Water Works Association publishes a report called Benchmarking Performance Indicators for the water and wastewater utilities in the United States. And when we first got a hold of this publication, we thought, gosh, this is exactly what we need. But turns out this publication is not free and anonymizes and aggregates a lot of data. And so what we got out of that particular publication was information that says the Southeast United States has this average value of energy intensity for drinking water utilities. But that doesn't tell us specifically what energy intensity is like for Atlanta, for example. It assumes that everything in the Southeast United States can be lumped together geographically speaking. Finally, there's some state level data out there. California does a really good job of keeping track of water and energy, simply because there are a lot of utilities that are sourcing water from long distances. And California is no stranger to drought. And so they have started collecting data at the state level. Texas has also started collecting data at the state level through the Texas Water Development Board, but those are only 2 of 50 states. So what do we do to reflect urban water data at a national scale? Well, when you don't have data, what do? You hire a graduate student and they spend their entire dissertation collecting data and analyzing data. So that's exactly what my now former PhD student did. His name is Chris Cheney. And he collected data through the best approach that we could find, which was submitting open records requests. This falls under the Freedom of Information Act, and any of you that are familiar with FOIA requests know that they don't make friends, and they are a formal way of requesting information from public entities. So public utilities are required by law to respond to these requests, and they can charge money for them, but they are required by law to respond within a specific amount of time. Not everyone responded to us. We didn't pursue any sort of challenge in collecting data, but this was a long endeavor and a very time and labor intensive thing. Each one of these dots on this map is a city that we sent a data request to. And our goal with this request was to first prioritize the largest cities in the United States. And then we wanted to have a representative from each state at a minimum. We started with cities that had population of 100,000 and above. And so that got kind of the first smattering of cities that received requests. But then we realized there were very large geographic areas that we didn't have any representation from. For example, Montana, North and South Dakota, we didn't have cities over 100,000 people. And so we then submitted requests to the largest city in the state so that we had some geographic representation beyond just the largest cities. And this is a high-level representation of the responses that we got. Note how none of these have a 100% response rate. And this is after the course of almost a year of submitting requests and corresponding with different individuals. So there's already some lack of data disclosure associated with requests. And one thing that we found was that wastewater utilities are more likely to respond than drinking water utilities. A few drinking water utilities responded that they were not willing to disclose any data. And by the way, the data we were asking for were how much flow do you treat and how much energy does that require? So pretty neutral information. But a number of drinking water utilities would not respond because they saw that as a security risk in disclosing that information. And so some of those non-responses are from utilities that had security concerns, and some of those non-responses were just plain non-responses for no reason that was reported. Within these pie charts here, we're also showing the temporal resolution of the data that we received on both flow and energy. And drinking water and wastewater utilities both are more likely to report daily flow data, which kind of makes sense. They are in the business of treating water or wastewater, and most operators and managers at those facilities have a really good handle on the flow that they're treating, because that's an important part of the process. What they had a less good temporal handle on was on energy consumption, which wasn't overly surprising, but some of the ways that we figured that out were interesting, to say the least. In requesting things like flow and energy data, my student would get spreadsheets with daily flow data. And then on the energy side, in one instance, got photocopies of utility bills for the electric bill in a stack that were mailed to him. And while that's useful in that it gives us information, it does also give us information on a lack of feedback mechanism in terms of managing resources. The operators at the plant have a really good handle on flow itself, but not so much on the energy that they're consuming, because the electricity bill was paid by someone in the accounting department without that feedback mechanism to the plant itself and to the operators in the distribution system. So we got this information, and what sense can we make out of it? Well, this particular map is for drinking water. The next map is for wastewater, and they're very similar scales here. So each circle represents a city that responded to our request. The size of the circle is the daily per capita drinking water on this particular map. The next map is wastewater. So flow is the size of the circle, and the color inside the circle is the embedded energy associated with that water, where the cooler colors are lower embedded energy and the warmer colors are higher embedded energy. There are several here that don't have a color, and that's because they either didn't report energy consumption data to us, or it didn't make any sense at all. So being virtually home in Missouri, we can pick on Kansas City a little bit. Kansas City did report energy data to us. And in the process of crunching the numbers, comparing things across all of these cities that we had data for, Kansas City's energy, embedded energy, was a couple orders of magnitude higher than any other observation that we had. And so what my student Chris did was call up his contact at Kansas City Water and say, this is what I'm seeing, and it's way different than everything else that we've got in these data that we've collected. Is there a units error, or is there a decimal in the wrong spot? Like something's weird. And the response was, well, that's what we've got. I don't know. So there's more reflection that there's not necessarily these feedback mechanisms of how much energy is associated with water and wastewater operations. Another thing that we took away from this was that things like the American Water Works Association publication that groups things geographically doesn't exactly make a ton of sense. And that's because, statistically speaking, there are no clusters that emerge spatially across these data. There's not much that we can say in terms of spatially aggregating data and still representing the underlying variability based on the numbers that we've got. There's no strong correlation in embedded energy, and there's no strong correlation in per capita drinking water consumption. Similar map, but this one is for wastewater, and we see that there's more data here, and there is correlation, spatial correlation, associated with the presence of combined sewers, which is to be expected. When a city has combined sewers, the per capita wastewater volume is expected to be higher than in a city that has separated sewers. And we've got more information on embedded energy here, but again, there's not a lot of spatial correlation across embedded energy in the context of these cities in our sample that we've collected. This turned out to be around 223, if I remember correctly, utilities across water and wastewater. And we ended up with representation from most states, and enough that we can see that there are large differences across space and not necessarily motivating the spatial aggregation. One thing that we learned that we weren't expecting at all was that energy intensity of drinking water varies with time, but not necessarily with the same pattern across different cities. So there's a sampling of 6 cities that reported monthly data for both drinking water volume and embedded energy. Drinking water is the solid white line in each one of these, and embedded energy is the dashed white line. And for some of them, we saw a trend that we would expect. Dallas and Oklahoma City, for example, down here in the bottom row, are trends that we would expect, where drinking water volume peaks in the summer, likely associated with lawn irrigation, and is lower in the winter. And we would expect the embedded energy to follow a similar trend because the pipes are the same diameter, they always have been. And as we're moving more flow through the pipes, we would expect to lose more energy to friction along the way. But we didn't see those same trends in colder climates. Anchorage, Boston, Colorado Springs, and Salt Lake City are here to show the other trends that we observed, which is a higher embedded energy in the wintertime as compared to summertime. The flow of drinking water in the summer is higher, as we would expect, associated with irrigation, but the embedded energy in the wintertime is because when we requested energy data, we purposely used the term energy and not electricity. And so some utilities reported all of their energy consumption, which includes primary fuels, natural gas, fuel oil in some instances, and other primary fuel sources. These utilities that are in colder climates use a lot of natural gas in the wintertime for heating facilities. And turns out that's not negligible. Previously in the literature, all of the energy associated with water and wastewater has been in the form of electricity, not accounting for natural gas used for space heating, which is a large component in some of these colder climates, especially on the drinking water side of things, where there isn't an opportunity to beneficially reuse biogas as there is in large wastewater utilities that are using anaerobic digestion. One of the last bits of data that we collected was non-revenue water. And this was a simple percent that we collected from different utilities. And this data set was actually easiest to assemble via Twitter. I'm happy to talk more about collecting data and some of the adventures that we had in finally getting the right person on the phone, most effective ways to collect data, which turned out to be snail mail, like a physical letter, and Twitter, kind of the bookends of communication systems. And in terms of non-revenue water, this is reflective of what we would anticipate in the urban water system, in that older systems have leakier pipes. All pipes leak, and the age of the system is generally strongly correlated with the percent non-revenue water. Some of these are really large. We're looking at almost 50% of the water that is treated at the treatment plant never makes it to a customer and is accurately paid for. So that could either physically leak out of the system or could be from metering inaccuracies. Or in the case of Chicago, for example, a number of residences still don't have water meters and are estimated based on square footage of a residence and number of bathrooms. So what we learned from this first question of how we characterize urban water systems is really that data aren't available and it's time and labor intensive to collect them, and that energy intensity of water and wastewater really depends on both primary and secondary energy sources. It's primary fuels like natural gas and electricity that are required for operating these facilities, and those vary spatially and temporally. When we put numbers to it based on embedded energies and non-revenue water percentages, non-revenue water requires the same energy as about 300,000 US homes. So it's small, but not negligible at all. When we're talking about a future where we have to be energy efficient and sustainable across many sectors of the economy, non-revenue water is some low-hanging fruit in delivering more water to customers and saving energy associated with that high-value resource. So moving on, our second question then was more about how does water and energy relate to these other flows in and out of cities? And this flow of materials in and out of cities is a concept called urban metabolism. And it's essentially treating the city as an organism, and we are then applying material flow analysis, which is an accounting methodology, to that urban scale. Some researchers have designated urban metabolism as a mechanism that is the sum of social, economic, and technical processes in a city. It is difficult to quantify some of those things. How do you quantify social processes in a city? And so urban metabolism is something that has been kind of morphing throughout time. And most of the studies that have been done in cities outside the United States. There are a lot of analyses in Australia and Canada and Europe, but relatively few studies in the United States, and a lot of them are only looking at a single city, a single location, and a snapshot in time. There's been very few that compare across cities with the same methodology. And when we think about urban metabolism, or if you want to think about it as your own metabolism, it's kind of the opposite of a biologic metabolism, right? I would want to have a high metabolism so that I can eat a lot of food and not store mass in a city urban metabolism, we want a low metabolism, meaning we intake less and output less. And there's changes in storage associated with urban metabolism that come from urban growth and other manufacturing processes that would happen inside the urban environment. The classic separation of materials coming into the urban environment really focuses on water, fuel, food, materials, and then any other goods that come into the urban system. And each one of those flows takes energy to facilitate that movement of flows. Then once those materials are in the urban environment, there's more energy associated with the waste that flows out of the city. And those wastes are typically wastewater and solid waste, but also air emissions. There's not energy really associated with air emissions unless we're working to capture and remove those emissions. And that's not really something that's happening at the urban scale. And so we really focused on material flow, specifically water and wastewater. This urban metabolism concept is something that uses a standardized methodology, and we worked on quantifying the urban metabolism across cities in the United States using the freight analysis framework data that are reported nationally, and then quantifying inputs and outputs of a city, not focusing on circulation within the city. And so this somewhat grainy picture here on the slide is the original urban metabolism study for the United States that was published by Abel Woolman in 1965. And so what Abel Woolman did was estimate the flow of material in and out of a city for a hypothetical US city of 1 million people. And it was really a pioneering paper at the time. It just got lots of citations in response. But one of the things that we noticed was it's difficult to understand where the data came from. Where did Abel Woolman get these data? Or was it not even data driven and instead was based on these underlying theoretical flows to support life in a city? And so what he quantified then is water and wastewater, which he labels sewage, food flows, fuel flows, and then waste out and air pollutants out. And the visualization here is actually a little bit easier to see on our recreation of the visualization, where each cube is 500 metric tons per day of mass, and water and wastewater, as expected, really dominate this mass flow simply because water has a lot of mass. When we put things on a mass basis, food and fuel are fairly small compared to water and wastewater, but all of these inputs are necessary for life in cities, and specifically life in sustainable cities requires understanding these flows. So this is Abel Woolman's results from 1965 on his estimated urban metabolism, again for a hypothetical city of 1 million people. And if we were moving toward a more sustainable urban metabolism, we would expect these inflows to decrease over time. And so my student and I quantified, using the data we'd collected, this same urban metabolism for the year 2012. And unfortunately, we did not see a decrease in urban metabolism. We actually see an increase in urban metabolism over the course of 50 years. And that increase is specifically focused on food and solid waste. So going between these two illustrations, water and wastewater are pretty close to the estimates that Abel-Wohlman had. Ours are based on measured and reported data. So that's a really great sign that we've got data to back up these same estimates from 50 years prior. The food and refuse from Abel-Wohlman's estimate have gone up significantly, and this is still for an average city of 1 million people using data across the United States. We're seeing more food coming in and more refuse coming out. What fits in that refuse or solid waste box is an interesting question for future research as to what are the components of solid waste. Are they mostly food waste? Research would tell us, yes, there's a lot of food waste that goes into that, but there's also other materials that are in solid waste. So how do we best move forward with sustainable cities? Focusing on solid waste is an element of low-hanging fruit in this perspective. So our estimate for the 2012 hypothetical or average city for 1 million people is not so different on the water side as Abel-Wohlman's original estimate. One thing we wanted to do was also understand the energy associated with facilitating this flow. The water and wastewater flows here are not to scale because otherwise the visualization looks really ridiculous because they're so large in mass flow. But the energy associated with facilitating these flows is dominated by water and wastewater, but there's also a large amount of energy associated with facilitating food flows. And a lot of that comes from energy-intense transportation systems and also refuse coming out as solid waste. By our estimates, a city of 1 million people using US average values across different regions requires almost 4,000 gigajoules per day to facilitate this urban metabolism. So another approach to smart cities is thinking about some of these flows and reducing the flows themselves and the energy associated with those flows. We also looked at things from a regional perspective, and at the regional scale, the Midwest is a really important region. And that's because Midwest is kind of the hub of flow throughput from different coasts. The food, fuel, building material flows are much higher than the national median. These bar charts are showing deviation from the national median. And those flows are much higher in the Midwest because we have a lot of foodstuffs that are being grown in rural areas, processed into food ingredients or final food products. Also fuels that are moving from one location to another or being extracted from local resources, and same with building materials. Wastewater is an interesting one when we look at it regionally, and a lot of that emergence of wastewater being above the national median is associated with the presence of combined sewers. The Midwest and the Rust Belt cities and some old Northeast cities have large combined sewer systems, and the mass flows associated with combined sewer systems become quite large, especially when compared to other regions with predominantly separated sewer systems. So all of this kind of sets up a future research study on things like material flows, especially those material flows that are moving long distances. We're generally not moving drinking water very long distances, certainly not as long of distances as we might move food, fuel, and building materials. And things like food and building materials are often coming from energy-intense transportation systems like trucking versus pipelines, for example, on fuel that can be very energy efficient ways of moving mass flows. So revisiting our question of how water and energy relate to other material flows in and out of cities, we see that water and wastewater fluxes really dominate, and that's because of the high mass associated with those materials. Water and food are particularly energy intense city inputs. And what that means is if we want to really focus on something like energy sustainability goals, it makes sense to focus on water and food also. When we look specifically at what's changed in US city metabolism over time, food and solid waste have definitely increased over time, and that represents areas of additional sustainability investment. These things vary widely with space, and there's a large important presence in the Midwest as a geographic hub for these different materials. So really a one sentence takeaway from all of this is that city sustainability extends beyond just thinking about energy or emissions. It also depends on water. It also depends on food. And it also depends on these other material inputs into cities. So if we want to have data-driven, sustainable cities, we have to think beyond just smart energy and start thinking about sustainability as it relates to these other material flows. I want to acknowledge my former student, Dr. Chris Cheney. He's now an assistant professor at the Air Force Institute of Technology. A lot of this work was published in his dissertation. He was supported by the National Science Foundation Graduate Research Fellowship, and we have other funding from the National Science Foundation that has really facilitated a lot of this work and made it possible. And one last bit, since you said you're recording this and potentially distributing to undergraduates, I have openings in my research group. We are this badass group here with masks, and it was cold that day, so we all look like we're kind of angry, but my students joked that this should be the cover of our hip hop album that we release. I've got openings for, I think, 2 PhD students starting in the fall. Probably the most relevant one in the context of chemical engineering is some really exciting work that we have National Science Foundation funding for understanding distributed chemical manufacturing. And my group is supporting in conducting a techno-economic analysis and spatially resolved life cycle assessment of these distributed chemical manufacturing operations, upgrading waste products using electrolysis and CO2 reduction technologies. The second option in PhD or MS plus PhD students I anticipate hiring, which this one's got, it should probably have a question mark by it simply because we are facing a very uncertain future with COVID and budget cuts, but we want to study water conservation and efficiency in residence halls and start to understand the impacts of infrastructure and also behavior change and ways that we can or cannot, we'll find out, influence behavior change related to water. So with that, I'm happy to answer questions. For anyone who might view this recording and have questions later, you're welcome to contact me via email. That's probably the best way to find me, or Twitter, I suppose, if you would like. There's a link to my group's website, which is where we keep links to all of our publications. And the papers that came out of this work are all linked there if you don't want to furiously Google them.
Thank you very much, Ashlynn. I'll go ahead and open it up for questions. So I had a couple to get us started. I guess the first question I had, you were talking about the metabolism of a city and what the ideal metabolism would be. I guess taking this as an analogy to humans, you said that we might all want a high metabolism. I picture that as being, so how active are you? Right. So if I have a really high metabolism, I might work out a lot, run a lot. If I have a low metabolism, I might lead a more sedate lifestyle. I guess I was wondering, is there an analogy that can be drawn for the metabolism, urban metabolism, and the productivity or the GDP of a given city? Is there a correlation there?
Oh, that's a really good question. I'm no expert on biological systems, and I think that might be an aspect where the metabolism analogy starts to break down.
Okay.
In that the metabolism of a biologic organism, yes, you would want a high metabolism so that you can be active and do all of those things, but that also requires a lot of inputs to support that activity. One of the important things that I think is a success really in the water industry and the water sector is that there's been a lot of decoupling around GDP and population growth and water consumption over time. We have had fairly flat water consumption over the last few decades, which is good because population has grown in that amount of time and GDP has grown in that amount of time. So to the extent that we can separate energy consumption and economic growth or population growth, and water consumption and growth are, I think, important factors for sustainability. Otherwise, the textbook economics examples of more is always better doesn't really work on a finite planet. Eventually we run out. Does that answer your question?
I think it does. I guess what I understood from what you said is that for water, there's not so much a correlation. It's the GDP has gone up, but water has stayed flat. And then you kind of loosely said that, if I understood right, it's difficult to make any sort of statements about the other feed streams, whether those are needed.
Isn't that also because of our commerce has changed, our commerce mix? I mean, we've certainly become more of a electronically driven economy versus an industrial economy. My question is kind of coupled or tangential to Matthias's is as we look at different heat transfer fluids, such as molten salts and others, how do you see that affecting the economy of water?
That's a really good question. The reason we've historically used water is because it's abundant and it's cheap, and these molten salts as a working fluid or heat transfer fluid are not cheap, or if they are cheap, they're not free. And in a lot of these water intense processes like electric power generation and manufacturing, sometimes those entities will pay for water, but oftentimes they're paying for the energy and the treatment to acquire water, not necessarily a per gallon price that you and I would pay on a city water bill. So from an economic perspective, gosh, I hate to say this, but I think we have to have dollar signs on volumes of water for everyone. But that then gets into interesting pricing questions around a resource that is necessary for life. So it's not quite as simple as just saying all water has to have a price. Yes, but all water also has to be affordable for the particular application, right? There's a whole bunch of context that comes into that.
I agree with you. I do think we need to have economic measures of water as we do for carbon, right? I mean, we're certainly moving toward those for carbon to really understand the impacts. And I think that's, at least in our country that is so capitalistic, we need to have those measures in economic terms. So I agree with you. Okay.
I hear you, and I agree. I also do a fair amount of work in nonprofits that work on things like environmental justice. And so that's why I hesitate to say things like all water should have a price. Yes, but it should also be affordable for everyone.
I guess this is a related question. You were talking to water as drinking water when you were talking about water consumption. From my understanding there, like for a given household, it's really a small fraction that we drink. We use a lot more water showering and maybe cooking than we than we drink. Do you have some idea of that large water block that you showed for the metabolism of a city? What fraction of that is for sustaining life, and what fraction is as a working fluid or as a washing fluid or other things that other uses water has?
That's a really good question. It varies spatially, and a lot of that is driven by how much water goes on grass. In some cities, in arid locations, 80 to 85% of the drinking water goes to outdoor irrigation. And in other locations, that's a much lower percentage. And that's where any given city is very different. There's not a lot of lawn irrigation for residential customers in Manhattan, downtown Manhattan, New York. But if we take Manhattan, Kansas, for example, there might be a lot of outdoor irrigation for lawns, because that's how we've built our cities, and that's how we live, for lack of a better term. How much of that is really necessary for life? A low percentage. At the same time, though, we have also built all of this infrastructure around one pipe in and one pipe out of the homes. We largely haven't dual plumbed homes such that we could have a really clean water source and a clean enough water source that comes into the home, such that I can flush my toilet with something that's clean enough, and I could water my grass with something that is clean enough. And if the dog drinks out of the toilet, he's not going to get sick, but we're still not going to drink out of the toilet. That percentage, at least based on work that we've done, we have some separate NSF funded work on residential water consumption and disaggregating that. Every household is different, but the actual drinking water is in the tens of percents and not approaching half. One of these smart water systems is on my house. And so I know how we use water. I didn't tell my grad student how we use water in my house. She told me based on the data, and most of our water is going to showers, because I have 2 little boys that take 40-minute showers. And we don't water our lawn. So from that equity and affordability and drinking water quality perspective, it's a low percentage, but it's not just drinking water, it's also hygiene and cooking and all of that. And then the luxury things like grass and pools and stuff. That was a rambling answer to your question. I apologize, but that's an area of research that we've been really working on to understand what happens inside the customer's boundary without barging in and invading the customer's privacy.
I think your answer was great. It gave me everything that I was looking for. So thank you. There is a comment or a question from a grad student, I believe. Did you find any of these results surprising? How did the US compare to other countries? Can you comment on that?
We did. There were a lot of surprising results. Surprising in the pure numbers we were after. I was surprised that natural gas played such a large dominant role in colder climates, especially on the drinking water side of utilities. I was also surprised in things that were kind of external to the research around the dynamics of collecting data and the disconnect between utilities and the academy. We often talk a lot about how utilities should be partnering with universities and vice versa. Universities should be partnering with utilities. And we started that data request process like good Midwesterners in asking nicely. That was our non-scientific approach to collecting data, was let me see if I can find a guy or a lady who knows someone who can tell me the answer to this. So it was very ad hoc, and it was very Midwest nice way of going about it. And we got ignored most of the time. We sent emails and we made phone calls and we left voicemails, and we often didn't get a response from those things. And that's why we then started implementing these open records requests. And we got so many people who saw that and were like, why wouldn't you just ask me nicely? Check your voicemail, man. We did, and you ignored us. So that was an interesting exploration into the human side of collecting data.
But where I'm located, at least part of my time, you know, this area behind me in the picture, up in the northwest part of this country, I mean, water policies are very personal, right? And everything you're stating is absolutely correct, but how could you sell it to the communities that live in and around the inland mountain region of Idaho and Washington and Wyoming, where, you know, agriculture is what we do. It is our livelihood, but water rights are a significant part of, you know, determining how well we do it.
Exactly. And there's a lot of disconnect between the Western United States and the Eastern United States when it comes to those things. In my office on campus, I have a postcard with two farmers. One has a shovel and one has a pitchfork, and they're swinging at each other. And the caption says, "Discussing Western water rights, a Western pastime." And I like it, well, because it's funny, but also because there's a dialogue happening. And in Eastern water rights, we have riparian water rights in Illinois. And so when there's a drought, we have no clue what to do, because there isn't that same prior appropriation list of who's in line and who gets how much water and in what order. We don't have that same solution. And so I don't think there's as much buy-in in valuing those resources.
Awesome. Thank you, Ashlynn. I think we better wrap up. I guess I'll stop the recording here.